Okay, we begin with looking at the types of materials, and you had a little bit of this to do with your assessment task, but we need to define them specifically. There are three different types of materials that we're going to have a look at. In your assessment task, you focus in on the fourth type, which was the superconductor. I'm going to now look at the conductor, the insulator, and the semiconductor. Okay? Right, so what is an insulator? Now, we know from our previous years of study that an insulator does not conduct electricity. Okay? But we now need to know why it doesn't conduct electricity. It's no use saying, okay, rubber's a good insulator, so is pure water a good insulator, but why does it not conduct electricity? If you add a little bit of salt to our pure water and make it impure, it becomes a very good conductor of electricity. Ask anyone who's accidentally electrocuted themselves in the bathtub. Okay, so what is an insulator? It's a material that obviously does not permit the passage of electrical current, and that means it has a high resistance. That's the definition really of resistance, is it resists the passage of electricity, hence its name. Now, I'm going to be using the words valence in a few moments. Now, can I ask an indicator, who is not a chemist among us? Okay, right. Yeah. So a valence electron is an electron in the outer shell of an atom which is able to be lost or gained or shared for a bond. Are we okay with those? These are the outer electrons that can bond. Okay? So the outer shell of an electron of an atom is called the valence orbits. And there are often, 5 or 6 electrons out there if it's a non-metal, or only 1 or 2 electrons out there if it's a metal. So electrons in the valence orbit, the outermost shell of the substance, are held tightly to the material of the atom. These electrons are involved in bonds, and they enable the structure, the actual solid that they form, to form a lattice. Now, let's be very clear on what a lattice is. And a lattice is simply a regular arrangement of atoms. And atoms do not come only in cubes. Okay, was one of the things that I've got from marking your assessment task is that you have this whole idea that atoms, the only arrangement a lattice has is a cubical lattice. Okay, they can be tetrahedrons, they can be pentagons, and so on. They can be even buckyballs and different. They're just different circular arrangements of atoms. Okay, a lattice is just like a brick wall, and brick walls themselves come in different structures. Okay, the ones that you have over here is a normal bricklayer's brick, so you have that structure. But there are different ways that you can arrange the bricks. Okay, you can have them some sticking out, depending on what you want to do with them. So, insulators, the bonds make up the lattice. The lattice holds those electrons nice and tight, does not allow them to go off freely. Okay? Are we okay with that? The second type, a conductor. A conductor is obviously, from its definition, it conducts electrical current. Okay, now what conducts is the free flow of electrons. So it must be that the electrons are free to move in a conductor. If they are free to move, then there is little scattering of electrons. So that means it has low resistance. Low resistance, remember, we have been talking about for a while that, I'll just take 5 seconds now. If I had a lattice, here we've got a lattice, I'm going to try and make it so it doesn't look cubical again because I think we think that it's cubical. Okay, there are bonds between all these atoms. Okay. Now those bonds exist, whether it be metallic bonds, ionic bonds, covalent bonds, or even hydrogen bonds. those are different types of bonds. What a bond is an arrangement or a sharing or an attraction to each other which holds them in a regular shape. Now, we are used to saying that an electron goes through and somehow collides with things. We use the word collide. So it might collide with an atom or collide with an impurity. Am I using the words that you're familiar with? Now, can an electron actually collide with a nucleus of an atom? The actual answer is no. Can an electron actually collide with another electron? No. They don't physically, like my hands slap together here, they do not physically come into contact. What happens is, as the electron tries to make its way in, it is pushed around and it is scattered, it is pushed. As it approaches another electron, as one electron here approaches this electron going this way, one has to move out of the path of the other because they're both negative charges, aren't they? So we are going to try and remove our words of collide. We are going to use the word scattering. So electrons no longer collide with the lattice, they scatter from the lattice. The lattice scatters them, or other electrons scatter them. Scattering impurities scatter them, make them no longer go in the direction that they were going in a few moments ago. As it changes direction, what happens to the electron? It accelerates in one direction or the other because it changes direction. Okay. Are we okay with that? I'm just trying to use the terms that we are going to be using. So let's move back to that. So as the electrons move through the conductor, they're not scattered as much as they would have been if they were trying to move through an insulator. Most conductors, as we know, are metals.
Sorry,
And okay, so electrons are not scattered very much as they pass through the conductor. We know that the path of an electron is always random. Okay, so there is a fast random motion that the electrons always have because they're trying to avoid every other electron that exists. This fast random motion, millions of meters per second is the motion of these electrons. Basically, the electron goes nowhere because it goes one direction, then it goes in the other direction, and then changes direction again. And overall, it goes nowhere until a potential is applied. After that happens, it starts to, even in random motion, it starts to drift randomly, okay, down towards the positive end. But normally, when a conductor is formed, electrons that are in the outermost valence shell, they're lost. And all the electrons, we call it the sea of electrons. And there's miles and millions of billions of billions of electrons free to move throughout the substance. So a conductor has a lot of free electrons ready to go wherever it wants to, whenever a potential is applied. Okay? Now, where are these electrons lost to? They were in the valence band, and then they've moved to this space between all the atoms. We're going to call that space between the conduction band. Okay, are we happy with that? These are truly still an orbit. They're considered an orbit around a nucleus, but they're not around a nucleus for long. They constantly join an orbit and leave an orbit and keep on going around. So these are delocalized electrons in a sea, and they are influenced by the lattice, but they don't stay in any specific orbit in the valence band for long. In fact, we basically say that the conduction band and the valence band become really overlapped. Any questions on that? Okay. We're going to be looking very soon at the term semiconductor. Now, a semiconductor is, by its name, tries to describe what it means. It's not a pure conductor like a good old metal, like copper, okay? But it sometimes conducts electricity, but sometimes doesn't. Actually, can I restate that? Most semiconductors are very good conductors of electricity, but sometimes they are even better conductors of electricity. Okay? And this conducting of electricity is to do with temperature. So as the temperature rises, we get a better conductor. So it's a material in which the resistance decreases as the temperature rises. As the temperature rises, that means more conduction, therefore a better conductor. At low temperatures, a semiconductor's resistor is quite insulative, so they're not exactly an insulator, but they resemble an insulator. Now, when we say low temperatures, what are we talking about low temperatures? We're talking about very, very cold, not like today temperature where it's 18 or so degrees, and that we feel that as cold. We're talking about low compared to a substance, which we are talking about in the minus hundreds of centigrade. Okay. At higher temperatures, a semiconductor becomes quite conductive. And in fact, in many cases, you couldn't tell the difference between the conductor and, say, a metal. Okay. The resistance, if you had to measure its resistance, it's somewhere between an insulator and a conductor, and hence its name as a semiconductor on the scale. Okay. Okay. So here are two, this one over here, this diagram here, please don't copy down, just looking at the resistance. What this one here says, let's make it so I can actually, as temperature increases, so temperature is going this direction, as temperature gets hot, so this is hot up here, hot, and this is cool. Okay. At hot temperatures, the resistance is low. And at cool temperature, the resistance is high. So as the semiconductor gets warmer, hotter, it becomes more like a conductor. So that's, and the actual shape of the graph is slightly hyperbolic, but it can be a variety of shapes. It doesn't have to be hyperbolic in that shape. It could be parabolic and so on. Okay, happy with those? Right, just before we go on to the three different bands, I have a diagram of the increasing conductivity of the three different substances. We have insulators down one end, and down this end here, on the other end, we have conductors. Right in the middle are the semiconductors. So as you come towards the right over here, you get more and more conductive. Okay, so that's just basically the spectrum of substances. Substances are not insulators or conductors or things. They share at different times, different states of these materials are conductive or insulative. As I just mentioned, you can make air conduct, even dry air is quite an insulator, but it can actually conduct electricity quite well given enough energy. The spark, we've all been zapped on a dry, windy day, and that means the electricity has passed through that dry air, even though the air is quite a good insulator. Okay? We can make certain substances stop being conductive by adding impurities to them. Say, for instance, iron, we can make it less conductive simply by putting in impurity and so on. So all of these substances can be altered in their conductivity. Okay, so please don't have the whole idea that honey is an insulator, therefore it's always an insulator. Can honey become a conductor? Yes, it can. We can change its properties somehow. Okay? Rightio. Why don't I choose honey? It's the first thing that came into my head. Okay. Okay, I don't know if it's an insulator or not. Okay, but the three bands. Now we're going to talk about the two major bands and then the gap between the two bands. And these bands is another way of saying orbit. So I'm going to give the definition first and then explain why we calling them orbits and bands. Right, the valence band. Firstly, is the atomic energy level occupied by electrons in the solid below the conduction band. So I'll explain all this in a few moments. I'll just read it out first and copy these things down. This band, the valence band, is equivalent in most cases, now I have to say in most cases, because we do have changes of this technology, these terminologies, is equivalent in most cases to the outer shell where the valence electrons are located before they are lost. Okay? So if I'm an atom which has 2 electrons in my outer shell, and I am just a plain old atom, then my valence band, my valence shell, is the one which has the 2 electrons in it. But once I have lost, I've given those 2 electrons away for bonding, my valence band becomes the one below it. It's always the outermost shell that has electrons in it. Okay? Electrons in this band are able to enter into bondings. Okay? And remember, there are a variety of different forms of bonding, and they have a different strength depending upon their situation. We have, I've got 3 written up there that we are quite familiar with, especially if you're a chemist. I probably should be more familiar now with hydrogen bonding. Chemists who have hydrogen bonding now. Metallic bonding, is that okay? Yeah. I say metallic bonding, covalent and ionic. As we know, ionic is a complete giving over of one electrons to another, and therefore you come together because you're attracted to each other's positivity or negativity. And a covalent, of course, is a sharing. This band can receive electrons from other electrons, from other atoms. So a valence is not just a donor of electrons, it can also be a receiver of electrons. If the atom has lost the electrons to form a bond, then the valence band is always termed the last full band, or the outermost complete set of orbits. Okay? That's the reason why the word valence, when we say valence electron, once those electrons are lost, then the band that becomes the valence band is the one underneath it. Are we clear on that?
What about if it's covalent and they're sharing?
That means that they're not lost. They're covalent. So both of them, the outermost the outermost shell is not always full, because sometimes the electron is on this atom, sometimes it's on that atom. Okay, that's the reason why the word covalent means that together they form a single valence band. Okay. Secondly, an energy gap between the next band, which I'm going to just zip up here for a few seconds. The next band is the conduction band, which I mentioned before, which is the band above the valence band. Between that and the conduction, the valence and the conduction band, there is a gap. This energy gap is, it's just an energy gap. Okay. Electrons, as you know, can jump from one orbit to another, can't they? Yep. So. So, if an electron can jump from one orbit to another, how does an electron do that, by the way? What's 2 mechanisms for it to jump?
Energy.
Sorry?
It gets energy.
Energy from what?
Light or photons.
Right, from photons. And electrons love photons, don't they? If an electron absorbs a photon, it jumps orbit. Okay, it goes to a higher energy level. Okay, and we know that this happens with thermionic emission. This happens with the photoelectric effect. It happens with fluorescence, and so on. And we're very familiar with this. Now, is it allowed to jump halfway between 2 orbits? No, it's an all or nothing. You can only absorb the correct, choicest, juiciest photons. The photons that get you to that next orbit. Okay? And that's how, remember how absorption spectrum work, don't they? Still doesn't matter. Too much energy, it jumps off the atom altogether, and it gets into the conduction band. So it still goes into another orbit called the conduction band. Okay, but it's still got to be the right amount of energy to get there. Okay. Okay, so the energy gaps are between the bands. An electron is able to move from one band or set of orbits to another if it has exactly the required amount of energy to cross the gap. It's got to be exactly. Einstein called it the all or nothing principle. Either it gets it, it absorbs that photon, or it doesn't absorb it because it's not the right size. Right, we now know it's one thing that can do is we can actually absorb absorb photons. What's the other way that I can jump? Well, you told me that you had to get energy from somewhere. Right, yes. The other possible way of getting from one point to another is thermal energy, getting heat. Okay? So heat is the second one. So it's absorbing photons or absorbing heat are the two ways that you can jump from one band to another. The most important energy gap is the one between the last two, which is the valence and the conduction band. The size of this gap determines whether the substance is going to be an insulator or a conductor or a semiconductor. Right, the last band of any interest, remember we only are looking at the outer two shells of an atom. The outer shell is called the conduction band or the valence band, depending upon a few things. So the outermost energy band of an atom is called the conduction band, and this band is not full. It can never be full. Okay? Can't get enough electrons. You can constantly pump more and more and more electrons into it. Okay, electrons in the conduction band are free to move in and through the solid. Hence, we call it the conduction band. Conduction is simply the motion or the free movement of electrons through a solid. Okay? If you are in this band, you can form part, if you're in a metal, you can form part of that, what we call the sea of electrons. And in metals, the valence electrons have moved from this band, from the valence band into the conduction band. Okay, leaving a whole band empty, and we go to the valence band underneath. I'll explain that in a few moments. This band, the conduction band, can extend beyond the atom. Okay, if you're in this band, you technically have left your atom, and this is like a shared band between all the atoms of the solid. It's a good way of looking at it, actually. Okay.
Can we get a current kind of?
Right. Okay. Now, to try and explain, what these bands actually are, this is the best way a physics professor explained it to me years ago, and it made a lot of sense. So hopefully, it will make some sense to you. At the centre of an atom is what? The nucleus. The nucleus contains protons and neutrons, as we know. Okay, so I just want you to imagine this is a nucleus, and we're going to have enough protons and neutrons there, so we're going to be an atom like, say, let's see, phosphorus or something like that. Okay. Now we know that around this atom is the arrangement of the orbits are in shells, aren't they? Okay. The first shell has how many orbits in it? Two. 1, 2. Now, I'm drawing circular orbits. We now know, if you're a chemist, you know that these orbits are basically probability shells. Okay? But there are not perfect circular. The electron can be is a standing wave somewhere with it. It's all P's, D's, and F's, and so on. Okay? But circle orbits are the easiest way to look at this. Okay? And I'm making it flat. Okay, flat is good. Okay, right. After the two orbits of the first shell, how many orbits are there in the second shell? 8. So I'm just going to go 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. There's 8 circular orbits. Are we okay with that? Then how many orbits are there in the next shell out? 8. So it's 1, 2, 3, 4, 5, 6, 7, 8. Now, how can an electron get from one orbit to another? It can absorb energy. What are the two methods of absorption of this energy? Right. So imagine you're an electron and you're in this orbit just there. Okay, you're just here, and you absorb the right photon. It's only a very small.
Oh, hi. Sorry, may I borrow?
So the electron wants to jump from one orbit to another. So it absorbs the correct photon. Just imagine it absorbs a radio wave. That's not a lot of energy, is it? So it might be able to jump from this little orbit here to just a little orbit in the same shell. As long as there's no other electron in that orbit, it's quite happy to go there. But if it wants to jump from this entire set of orbits, which I'm going to call a band of orbits, you see how it's a band, okay, to another orbit, it's going to have to absorb a bigger photon, isn't it? And if it does jump from here to here, then it's got to go exactly across this band, this gap. Can it land halfway and then just absorb another one? No, it's all or nothing single quantum leap. That's what the expression of quantum leap meant. It must be a single jump. Okay? So this is a forbidden gap. This gap is not allowed to be, you're not allowed to end up in it. You've got to end up in the other set of orbits. Are we okay with that? Right. After this set of orbits, there is another set of orbits straight after that. What's that? How many orbits are we now? It's 8 again. Yeah. After that, there is a transition. Oh, we have to transition the orbits. The next one's 32. Okay, possible orbits. Okay, but let's just say that we've only got 4 electrons out there. Okay? I can't remember. Are you trying to count the number of?
2, 8, 8, 16.
2, 8, 8, 16. So that should have 16.
Yeah, it could have 16.
Yeah. Let's not complicate it. Okay. Okay. What I want to do now is I want to use a bit of a rubber. I'm just going to rub it out, and I'll just. Oh, it's too small. Okay. And I'll rub this one out. Okay, so all you are seeing now is a set of orbits in a thin stripe pattern. Okay? We call each of these a band. So this is the innermost band. Then there is another band here. There's another band here. There is another band here. And there is another band here. Okay? This band over here is totally and utterly full, isn't it? It's got 2 electrons, you can't put another electron in there. Is this second band here full? Is this one here full? The outer 2 are the only ones that may not really be full. Okay? So this here, the outermost band is called the valence band. Okay, in this case, it's got 4 electrons in it. Okay? So this is the valence band out here, this is outer shell. Now, I'm going to see if I can get this to work. Before I do that, if this has got 4 electrons in it, if an electron is in here, put it in here, an electron. Okay? If it gets enough energy, what can it do? It can jump from here into the next band up here. Is there anything in that band officially? No. This is officially really off the atom. But this band up here, if it gets up to here, this imaginary band or possible orbits that doesn't really exist because they're off the atom, this is called the conduction band. So when we're in a few more moments, we're going to be talking about only these 2 bands here. Those 2 there are the only 2 we want. And we're going to turn them vertically. Okay? So we're going to look at them going up. Okay? We are not going to be interested in all the other bands and orbits below because they're all full and they do not involve themselves in bonding at all. This is the valence band and this is the conduction band. And this between them is the forbidden energy gap, or just the energy gap. Okay? Why is it forbidden? Well, it's forbidden in all cases. You can't land here, here, or here, can you? All energy gaps are forbidden. They're zones that you have to actually pass all the way through and jump from one to the other. Okay?
And is there an energy gap between the valence band and the conduction?
Yes, that is just there. Okay. So in a few more moments, we're going to be looking at what we call band structure diagrams. And I'll just get a nice wrong colour on there. Nope. Okay, a band structure diagram is simply a rectangle which will have in it something like that. Okay? It represents the two outer bands. This will be the conduction band. I'll just lift this pen a bit bigger. That's the conduction band there and the valence band there, and this is the energy gap here. And all it is I want you to imagine is that this here is a whole series of orbits. Okay. This out here is a series of possible orbits that are shared by all the atoms in the solid. If you are an electron and you can move from here up to here, you are lost from the atom and are free to conduct electricity. Okay? Are we okay with that? But all I want you to get used to this diagram is simply because it's a quick and easy way to draw things. So let's have a look at the few. The first, actually, I'm not going to start with the. I'm going to start with the insulator. Okay. There is our insulator, and here is our band structure diagram. I'm going to put a rectangle around the whole thing. Okay. Okay. The upper band is called the conduction band, and the bottom is the valence band. Okay. Electrons, if they want to go from here to here, how big is that energy gap? It is a large energy gap. Okay. How much energy do you need then to move an electron from the valence band to the conduction band? A lot. Are these energies freely available for this electron to move? No. Okay. So that's how to read these diagrams. Okay. So on the diagrams that I've given you, let's go back now and have a look at the other two. Now, the first one is the conductor. Okay? The three bands exist. Sorry, the three parts exist. Conduction band on the top, valence band on the bottom. Where is the energy band? Well, the conduction band is so close to the valence band that the energy levels are actually shared. They actually overlap. So there doesn't actually exist an energy gap at all. So electrons can freely move from the valence band to the conduction band with little or no energy. Okay? So please have a look at the diagrams I've given you. Okay, on those things, and you're copying them down to those diagrams. So how easy is it for an electron to come from the valence band to the conduction band? Very easy. It's really mandatory for it to move. Oh, yes. Yeah, just on that diagram there, you'll see how there's energy gap. Okay, no overlap. Yeah, we know that they are overlapped, but we just have a line and have the energy gap is so negligible. Okay. 5 more seconds. The other one is the semiconductor. And once again, conduction band on the top, valence band on the bottom. What's the size of the energy gap? It's small. So given enough energy, heat or photons, can an electron jump from the valence band to the conduction band? Yes. And finally, going back to the insulator, have a look at the size of the energy gap now. Okay? Rightio.